So I'm gonna start the presentation. Okay, so that's it. Okay, so let's first get the idea of what a floating object is. So think about an object which is solid, and we place this solid body on the water surface. So this body is, the weight of this body is supported by the buoyancy. All the weight is supported by the buoyancy, and the body doesn't get submerged. So that's a solid body. The material is solid. That type of the material is solid. It's not fluid, and it can rest underwater, and its weight is supported by buoyancy or the hydrostatic pressure. So in this case, we have a floating body. So at the very earliest stage, now we've got the idea of the floating object. But let's just get another idea about marine vehicle that you might have. You might be familiar with it, but let's again get an idea about it. So any solid body, again, in the ocean or in water, in the sea, that can move from one point to another point under action of any force, but its weight is supported by hydrostatic pressure or hydrodynamic pressure or aerodynamic pressure, or aerostatic pressure is a marine vehicle. So in general, a marine vehicle is a type of solid body that can move from one point to another point while its weight is supported by fluid forces. So it's not just hydrostatic pressure. So it can be aerodynamic, it can be aerostatic, so, and different types of fluid forces. So now we have two different ideas, and we know the differences between these types of bodies. But by the way, they're both in the water, and they might they might be subjected to water waves. So now let's get another idea. So about water surface and surface waves or gravity waves. So assume that we have two different types of fluids. We don't have any motion, any fluid motion, and these types of fluids are not reacting with each other. So there is a surface that's dividing the domain into two subdomains, and we have fluid in each of these subdomains. The interface that's dividing the domain into subdomain is the surface, the interface between these fluids. And in the case that these two fluids, one of them is air and the other is water, the interface between air and water is the water surface. And you have water surface in, I think, 74% of the Earth, yeah? I think I'm right about it, sort of right about it. So wherever you have air and you have sea, and you have, of course, air-sea interaction, you have the water surface over there. So that's the surface that's dividing that's separating air from the water. So what about the surface waves? What are the surface waves? What are the waves that I think you have seen yesterday in some lectures? The surface waves or gravity waves. So when we want to define them, we think about the pressure and the waves. So when we have any perturbation on the water surface, we have waves that are generated. So, and what are these waves? These waves are the vertical movement of the water surface that we have already learned about. So when we have the vertical movement of the water surface, so we have the water waves, we have the gravity waves, and waves are propagating. So they're propagating and they're transporting energy for us. So not for us, just they're transporting energy, and energy is being carried by them. So that's what the surface wave is. So of course, you know, we have different types of waves in the physics. It can be acoustic wave, it can be cable wave. So, but in all of them, we have a wave that is being carried. So, and in the case of the surface waves or gravity waves or water waves, whatever you want to call it, so we have the wave motion, which is being generated on the water surface, and is moving on it's moving through water, propagating on the water surface. So just I think you have seen it before, but just to give you another idea. So whenever we want to have the solution for the motion of any type of the wave, we need to solve the partial differential equation for the, for the type of wave. For example, for the case of the cable wave that you have seen in partial differential equation or engineering mathematics. So you just need to formulate the problem and just have the partial differential equation. For the case of the water waves, when we want to formulate the wave motion, so what we do, we use some assumptions and I'm just telling you these assumptions in a very simple way. So we assume that fluid is rotational, and we assume that the wave height is very small, and also we assume that the motion is periodic. So what we get is a solution for the water wave and for the wave motion that we get on the water surface. And you can see the water waves that we get on the water surface when we have got the perturbation and when we have got periodic motion. So we got water surface, and we can have a solution over here, the solution of the water wave. And we have got wave number and wave frequency, both of which appear here when we have a cosine function that's telling us that the waves are going to be periodic, and both in time domain and both in longitudinal direction. And we have and the kx minus omega t, we call this one the wave phase, and it's changed over the time, and the speed of the change of the phase, we call it the phase speed. But now let's talk about something a little bit more important than what we have talked about till now. That's the dispersion relationship. So again, it doesn't matter what type of wave it is, what type of the wave you're dealing with. Any type of wave that exists in the nature, for that wave, we have a specific case of dispersion relationship, and the dispersion relationship relates the wave number to wave frequency, and it depends on the environment where you have the waves. Is it a cable? Is it an elastic body? Or is it water? Okay, so for the case of each of these environments, you have got your own dispersion relationship that relates the wave number to wave period. And for the case of the water waves, when we have surface waves and waves are propagating on the water surface, we get the special dispersion relationship that you see here. And of course, if you come back over here and have a look at here, we can compute the phase speed by using omega over k. So, and we have got omega over k. So by using the dispersion relationship, we can compute the phase speed, and the phase speed is telling us that how the phase is being changed at any point when waves are propagating. So, but let's think about something a little bit again more important, and that's dispersive. So we call waves, we call an environment to be dispersive or non-dispersive, depending on different situations. So when waves are propagating in any fluid or solid environment, and when the phase speed is a function, in the case that the phase speed is a function of the wave frequency or wave number, the environment is dispersive. Otherwise, the environment is not dispersive and is non-dispersive. And it's very important for us to know about it. And to give you an idea, the wave motion in a cable is a type of non-dispersive wave, but wave motion in solid bodies like elastic body is a kind of dispersive wave. But what about the water waves? When we have water waves, it depends on the depth of the water. So in the case that depth of the water is very shallow, we have a shallow environment, water condition, water waves are non-dispersive. Otherwise, they are dispersive. And this comes from this dispersion relationship you can see here. So if the tangent hyperbolic of KH, so converges to KH, which happens when KH is very small, so the dispersion relationship is changed to this relation, and you get the phase speed as this. And as you see here, the h is wave depth. As you see, the phase speed is just a function of the gravity acceleration and the water depth. And it is not a function of the wave number or wave frequency at all. So it's shallow water condition where waves are non-dispersive. And you can see that water waves can be both dispersive and non-dispersive. And this shows us that how complicated the physics of the waves in water environment is. So just to have a very quick look at the effects of the waves on rigid bodies. So waves can cause some motions on rigid bodies. So they can cause motions, and you need to study their motion. These motions can be something like oscillations, or they can be drift motions. So they can be different types of motion, or even they can be elastic motions that Lo-Feng, I think, has talked about it to you, or he will talk about them to you. And but in another way, in another beautiful way, body can also affect the waves. It can scatter waves, it can attenuate the waves. So when a body is exposed to water waves, any solid body, any floating body is exposed to water waves, it can attenuate the waves. So, and in another way, it can affect the dispersion relationship under it. So if we have a solid body, under the solid body, the dispersion relationship might be changed. Just think about an ice flow or a viscoelastic oil cover on the water surface. When waves are propagating on this surface, on the covered surface, the dispersion relationship is changed, and suddenly the wave number is changed, and as a result, phase speed is changed. So we have two different types of effects when we're talking about interaction of solid bodies with waves. To give you another idea, in hydrodynamics, in marine hydrodynamics, when we're talking about the dynamic of floating bodies and interaction of these floating bodies with water waves, we usually talk about two different types of problems. So we divide the problem into two sub-problems. One is the radiation problem, and the other one is the diffraction problem. And the one that we care about today is the radiation problem. And you can see that the word itself is talking about the problem, radiation. So it's like radiation of waves from a body. So radiation itself just concerns the motion of a floating body, and it doesn't have anything to do with the water waves. But it tells us that how a floating body, when it's moving and oscillating on the water surface, can generate waves, and in response to its motion, fluid can generate some forces on it. Okay, so, and just think about a body in the ocean, or just think about a solid body, a solid rigid body. It can have 6 motions. Yeah, so this body can generate 6 motions, and here it should not be Fij, it should be just Fj. So I'll correct it later for you. And just this body can have 2 different type of forces, which are added mass forces and damping forces. And added mass forces are the forces due to acceleration of the body at any moment, and the damping forces are the forces due to generation of the waves around the body, and they're very important for us to know them. So if we know all the forces acting on the body due to any of those motion, any of those 6 motion that body can have, then we can formulate the motion of a floating object in 6 degrees of freedom in the frequency domain in a very simple way. So we can just get a very simple algebraic system of algebraic equations, and we can just solve this equation, and we can get a displacement vector by just having the value of the added mass and damping matrices of the body, and just these added mass and damping added masses just depend on the frequency of the body. So by the way, so I don't want to make it very complicated for you, just to give you a very a very simple idea about it, simple way that we can think about it. When we're talking about a floating body, like this floating object that we've got over here, this floating object can have motion on the water surface. Don't think about waves. It can have motions on the water surface, and while it has motion on the water surface, it can generate some waves around it. So it's like a wave generator. It can generate waves around it, while water, in response to its motion, is generating some forces on it. on the solid body, and these forces can be due to acceleration of the body at any moment and due to the waves that are generated around the body at any moment. So, because this body, for example, is having an oscillation, is having something like harmonic motion in vertical direction, yeah? So at any moment, it can have a different value of the acceleration and different value of the velocity. So it can have different, so we can have different added mass and different damping forces at any moment. So by the way, so if we solve this problem, so if we solve the radiation problem for the case of a floating object, so we can use it to solve its real motion in the sea. So we don't need to solve its dynamic in the wave. So we can use the radiation, the simulation of the radiation problem to solve this equation, and we don't go to solve a real 60 OF problem. That's how it works. So we have 6 different radiation problem for a body. We solve it, and then we get the added mass and damping matrices, and then we solve the problem for the body. By the way, and now let's think about it even in a very, very, again, simplified way. Let's think about a 2-dimensional section. So it works for us, and we can solve just the radiation problem around a 2-dimensional section. And we assume that that is a section of a very slender body, like a ship, like a very large floating structure, or some types of very giant bodies you can see in the ocean. And in this case, you just solve the problem for the case of a 2-dimensional body, and you have the simulation or the solution of the problem around the 2D body, and then you extend it in the whole direction of the body as an integration. So you get the, for example, the full added mass or full, damping, the 3-dimensional added mass or 2-dimensional damping forces acting on the body just by using the 2D values, 2-dimensional values. So this is the way that we use OpenFOAM to solve the radiation problem for us. This is the idea of solving a problem in fluid dynamics to get the solution for the radiation problem and to use it for solving a dynamic problem. So in this way, we can use OpenFOAM. We can use OpenFOAM to solve the radiation problem for us in a very, very simple way and in a very fast way. So we'll see how it works. There is another way that you simulate the real wave-induced motion of a body in 60 OF or in 3D OF in 3 degrees of freedom that you have already learned about it in the, I think, yesterday about dynamic using overset. So dynamic simulation using overset. So we are not going to talk about this one today. So, but how can we do it? So the way that we do it, we use a very, very useful tutorial in OpenFOAM that is related to multi-phase library of the OpenFOAM. And the one that I'm using is, I'm using the tutorial of the OpenFOAM 1806, but you can find it in the next versions as well. So there is a example in OpenFOAM called oscillator box, something like that. I want to show it to you. I can show it even to you where it is. This is here, yeah. So this is a multi-phase, and you've got it here. So there's a solver named potential free surface foam, and I just got the example from here, potential free surface foam. Okay. So what is this potential free surface foam? So it solves a multi-phase problem, not a real multi-phase problem. It solves a single phase problem by considering a free surface for it. So we've got a free surface, extra free surface boundary condition. And in this case, for the case of the problem, without considering 2 phases, like one phase for air or 1 phase for water, we just assume 1 phase for water, and just we set the opposite phase to be free surface. It's how we solve the problem when it's rotational, when it's something like ideal fluid. But we can use it here, but unlike the ideal fluid flow assumption, here we solve the Navier-Stokes equation. So the fluid is assumed to be viscous here, and Navier-Stokes equations are solved, and the free surface boundary condition is simulated and computed. So the problem that we're going to solve here now is a very simple problem. So we have got a floating object, also you can call it floating box here. This floating object starts oscillation in vertical direction, and it generates some waves around it, and it comes from the problem. Yeah, we call the problem radiation. So it radiates some waves around it, and we can measure these waves and see whether this floating object can lead to some radiation of waves or not. So let's have a look at the problem. I've got a folder for it over here. Okay, so that's a static. Okay, so what we do first for this problem, we generate a geometry of the problem using the block mesh directory. It's a very simple geometry. So just defining 8 points, 8 corners for this big domain, for this big rectangle. And just we define, as you see, I didn't define it, it's just the tutorial of the OpenFOAM. So there's a free surface boundary condition. That's the upper edge, and we have got 2 ends in the right and left. Yeah, on the right and left, which are the walls, and we have got the bottom wall, which are all the walls of the boundary, and we've got just front and back, which are empty. And look, we have got floating object here, but it's an empty one at the current time. So there are no faces defined for it. So that's the block mesh directory. So but we need to have the floating object over here. So how do we do it? We just use the toposet directory. So we use a toposet directory to exclude the box from the domain, and just what we do here. This floating box is going to be replaced on the floating object. So on the surfaces, the patches of this box going to be included in the floating object. So if you have a look at here, so we just use the toposet, and we just use the band, and we set the boundaries of that box that we are excluding from the domain to be we are setting those boundaries to be the floating object patch. So this is how it works, how we generate geometry for the problem. So it's till now. And then what we do here is that we want to know what type of what type of condition gonna govern on our boundary. So generally, we have got just pressure and hydrostatic pressure, hydrodynamic pressure, and velocity field. So we have got 3 fields, but you know that these hydrostatic and hydrodynamic pressure are both just pressure fields. Just they're divided into 2 different types of pressure. So the most important thing that we should know here is that for the case of the hydrodynamic pressure on the free surface, we have got a boundary which is called the wave surface pressure. This one sets the air-water boundary condition, and it provides the free surface boundary condition. It helps the solver to compute free surface elevation and water waves around the body, or on the upper edge of the domain, on the free surface boundary. So you have got just walls. So on the walls of the domain, you have got the 0 gradient condition, and you have got the floating object, and on the floating object you have got this the specific boundary condition for satisfying the pressure on it. And let's go for have a look at the velocity field. So let's go back to here. I told you that for the case of the problem, we want the floating object to have oscillation in vertical direction. But how can we do it? It's very simple. So if we come here for the case of the velocity, field, again we have got the specific boundary condition for the free surface, which gives no shear stresses on the free surface. We can't have any shear stress on the free surface, and no normal stress. I'm sorry. And in addition, but for the case of the floating body, we prescribe a type of oscillation motion, and it is defined by velocity. So we define the velocity to have a fixed value, and this fixed value is prescribed over here. So at any constant time, the value is prescribed, and the value on the wall is something harmonic with a frequency of 1 hertz. Yeah, 1/1 second, 1 hertz. And we have got the amplitude of the velocity in the normal direction, and the scale and normal direction of the velocity. So we prescribe the velocity for the case of the body. We prescribe the velocity field on the body. So that's going to be the boundary condition at any moment. So it's prescribed, and that's it for the velocity. Yeah. And now let's go and have a look at constants. So the most important one here is G, the gravity acceleration. So it tells the direction of the free surface. Yeah. So if it's in Y, so you can have waves in Y direction. Yeah. So it's in Y direction. So it's in negative. So it's negative 9.85, and you've got gravity acceleration. So if you put it here in Z, so you're going to have waves in the direction of the Z in the third direction. So you should think about your boundary. You should think about your geometry and define it in a way that you're going to have your height in Z direction. But for the case of the current problem, we have got our height, so vertical, we've got the height, and G in Y direction. So as you see, you have just turbulence properties and transport properties that you use for fluid flow, and just we set the problem to be laminar here. You can set it to be turbulent, and you just define the viscosity, and just we define the viscosity of the water. And it's very easy. You can just then you can do whatever you do for other problems. For FV scheme and FV solution, you can use different schemes to do the decomposition of different terms, discretization of different terms, the transient terms, the Laplacian terms. They're just numerical techniques, and your CFD knowledge, you can use whatever you want. And you have got the methods for solution of the problem. As you see, you have both pressure and you have velocity field. These are both the two fields that are going to be solved, pressure and velocity. You don't have any free surface, and any simulation for free surface. Free surface is just computed by having the values of the velocity and pressure. And as you see, just an algorithm is used to solve the problem, which is the Pimple algorithm. You can set it to be whatever you want, and just that's it. So, and just you use Control-D to solve the problem, and you use the solver that I just told you. It's potential free surface foam. Just solve the problem, and just you can set the Cron number, or whatever you want for the Cron number. Just you should use a correct value to have to get stable simulation. And you should avoid having very large values. Yeah, it's just your CFD knowledge. And also you can use a function to get force and something like pull height, that I'm not interested in it, by the way, but you can use this force function, and you get the force acting on the body at any moment. So, okay, then you can solve the problem very easily. So what I do is just set all run, and the problem runs, and you can see that how fast this simulation is, because it's just a single phase flow. It's very easy for my computer, for my machine to solve the problem. It's even not parallel. So you get the simulation for 20 seconds in 20 seconds of computational physical time. Just, you see, it's very fast. So by the way, you get the simulation, and while I'm using OpenFOAM 18, I use OpenFOAM 5 for 2018. I'm using OpenFOAM 2018, but I use OpenFOAM 5 for my PowerFOAM, because it's a little bit mixy over here on my laptop. So just let's show you something interesting over here. At any moment that the problem is being solved, we have an output over here, and look, we have something new, zeta. This zeta is water surface. And look, in the internal field and the whole domain, the value of zeta is 0, but on the free surface, its value is non-zero. And in y direction, it's just non-zero. In other direction, it's 0. So it's how we get water waves. So you see, on the first surface, we have different values, and it differs from one point to another point. Again, on the wall and the floating object, it's just 0. It's just created by the solver. So as an output, you have got also you've also got zeta at any moment. Just let's have a look. Then then you just get the simulation of the problem. Yeah, that's velocity field on the body. Okay, pressure. Oh, that's let's see. This one's hydrodynamic pressure. It's a bit more interesting. So you get the simulation of the problem, and just you're thinking about water waves. How can we get the water waves? How can we see the water waves? First, you can see that pressure pattern. It's showing us that we have got waves here. So peak to peak, peak to peak. But how can we see it? We can use the zeta over here in OpenFOAM. And if I just switch to zeta, you can see that there is a crest over here, which is progressing, and there is a minimum point with the lowest level of surface elevation. Okay, so this is how this solver works for you. You can get water waves and you can get motion. You can get fluid motion in the whole domain. But let's do something a little bit interesting. So I talked to you about the dispersion relationship in the water waves, but just try to do something here. I just got the output for you. That's how I get the free surface elevation. I just sampled the data on the upper boundary. I just closed it. Let's go back here. Oh, 5. Yeah. So if you come here, I don't know. What I did on this upper surface, on the free surface boundary, I just sampled the value of the zeta at every single time step, and I just plotted it for you over here. So you can see that at a single point, the time history of the waves is plotted over here. And you can see that we have waves that are generated, and finally, yeah, the wave is generated and you have it at a single point. The body is oscillating and you have got waves that are generated, and so finally you've got the wave. And look at over here, I've also sampled the water surface elevation at I think it's the last time step of simulation. And I have just got the water surface elevation over the longitudinal direction. And you can see that water waves are generated around the body. And the peak to peak distance is 1.57. And this value is not exactly nearly equals to what the dispersion relationship gives to us. So we can see that the solver satisfies the dispersion relationship, and it's working very well, and we can use our simulation and get some results that can be a little bit interesting for us and see whether it works or not. But let's go to another example. Let's just make the problem a little bit different. Let's make it sort of shallow, okay? So let's make it a shallow water condition. So in the previous problem, we had the water depths to be something like, we set it to be something like 1 meter. This is y direction. We set it to be 1 meter, but in the current problem, we set it just to be something like 12 centimeter. Yeah, so I set the higher level to be 1 meter and the lower level to be 0.88. So now the water height is 12 centimeter. But just for the case of the topo set directory, I set the box to be a little bit tinier because I want to fit it in the domain. So I just did the same thing, just change the domain. I want to check something with the, oh, it's not working. I want to check something with the, okay, PWD. I want to check whether it works for the case of shallow waters or not. So again, get the simulation, and you see that's very fast, and just let's have a look at my 005 perform. Okay, so I can get it over here and just that. So let's get this too. Okay, so again, you've got the body motion, the wave generation around the body. Let's switch to zeta. You can see that waves are generated. Or let's have hydrodynamic pressure over here. You can see that how shallow water condition can affect water, the water surface generation. And you have water waves, and you can see that waves are generated on the upper boundary. So that's again zeta that I set over here, and I can see that, okay, waves are generated. So that's it for that. So, okay, now let's have a look again at something. We have got the output over here. So that's the output. So example of free, again, I have got the example of the free surface over here. So it's a time, it's a time history of the slideshow from, okay, slideshow from current slide. Okay. Okay. Oh, slideshow should be here. Okay. Slideshow from current slide. Okay. So you have got the time history of the waves again at the point. It's just near the body, and you can see the free surface pattern at the last time step. And you have got the longitudinal direction and free surface elevation. And this time, you can see that the peak-to-peak distance is something around a little bit smaller than 1 meter. And what dispersion relationship of the shallow water condition gives you is something like wavelengths of 1 meter. SQRT is, the phase speed is 1.0 meter. So in this case, SQRT of GH is 1 meter. So we may get a wavelength around 0.998 meter. If you go through the equations over there, you can get it. By the way, so you see that the shallow water condition affect the dispersion relationship, and you get shorter waves as we predicted. Okay, let's go a little bit forward and make it a little bit different. So what we have done till here is something like, static. We don't have any dynamic motion, but we're talking about the radiation. Let's make it a little bit different here. What we can do is that we can have dynamic motion. So we have a static motion. We just prescribe some sort of velocity field motion. So we set the velocity field to oscillate it around the body, and we're trying to, reproduce oscillation of the body by using a static point of view. But let's do it in a dynamic way, in another way, which gives us dynamic motion. So how can we do it to have the real dynamic in the whole domain? Well, we can use another library, another type of. So over here, again, it's just a part of OpenFOAM tutorials. It's come here. When you come to multi-phase, you've got it over here. Yeah, we had a potential free surface form. Now we have got the potential free surface diam form. What it does for us, it just allows us to have also dynamic motion in the whole domain. So we can see the difference here. Yeah. So let's have a look at it. Again, this time let's go back to the same problem that we saw at the very early stage here. So we had the problem over here. So let's do something that the body starts moving in the vertical direction. How can we do it? Of course, I haven't done it. It's a part of the OpenFOAM tutorial, but we can use it in our own way, in the way that we want. By the way, it's the same problem. You see, it's again the same domain. And you've got the free surface boundary, you have got the floating object boundary, the bottom wall, and the right wall, and the left wall boundary. And again, you have the toposet directory that excludes the box or the floating object from the boundary, from the domain. And in this case, we have another toposet directory that just is used to get the in addition to getting the floating object and excluding it from the domain and setting its surfaces to be the floating object, we use another typoset directory over here to just prescribe the bottom of the floating object. So we want to prescribe a vertical motion for this bottom. So then what we do, we come over here first. So we have those three previous constant properties we had already got, gravity, transport, and turbulence properties. And just we add the dynamic mesh, not me, I mean, again, OpenFOAM has done it for us before. The people who were developing OpenFOAM just did it for us as a tutorial. So we've got it over here. So we define a new, we define the dynamic motion through this type of dynamic motion solver, that's displacement Laplace film, and just use the library of the motion solvers. And what it does, we can use this type of the motion solver to prescribe motion for the body. And when we come to the initial condition, to the zero folder, what we can do here is that we can see that there is another directory here. That's the point displacement. So we've got the pressure and the velocity, which is going to be the same thing. We'll talk about the velocity later. Just for the case of the point displacement, as you see, we have got floating object. On the floating object, we're saying that, okay, we have got normal slip in the x direction, not in the y direction. And also for the case of the floating object bottom, which we define in the second toposet directory. So we're defining an oscillating displacement that's coming from the dynamic motion solver, dynamic motion library we're using. And just we defined omega for this one. And here omega is just, how can we do it here? Omega is 2 pi, okay, am I right? 2 pi f. So that's it. So it's now again the frequency of 1 hertz, yeah? So yes, it's nearly frequency of 1 hertz. And just we have the amplitude of the motion. So in the previous example, we were using velocity to force the body to have oscillation. This time we're using the real displacement. So look, this is displacement, so it's different, yeah? When you have, just to tell you how it works, just U is a omega, okay, cosine of theta, okay? So that's the difference between U and A. So in the previous case, when we were prescribing the value of the velocity, so we were assuming that, okay, we know omega and we know R and we know A, and just we define U in this way. Okay, by the way, so let's do this one. Okay, so just for the case of the velocity field, we set again the boundary condition over here. And okay, this time for the case of the whole walls, all the wall in the side and the wall in the bottom, we define the no slip boundary condition. And for the case of the floating object, so we defined the boundary condition of the moving velocity. So, and that's it. And we can set the problem to be solved here. So let's see whether it works or not. Okay, it does. And again, you see it's very fast compared to the other tutorials of OpenFOAM, like the ones that you can find in Interform. For the case of the dynamic motion, yeah, you've got dynamic motion in here, I think. You've got dynamic in interdial. Where is it? I'm looking for it. Oh, here, yeah. For the case of the floating body or bottom propeller, they're going to be very slow. But yeah, what we did here, we just, okay, solve the problem very fast. Okay, so let's have a look over here. Perform, and let's see what happens here. So what happens here is that, okay, let's just get the pressure and U and maybe zeta. Okay, I can also get the cell displacement. Okay, so that's the domain again. You have excluded the body, and look at here. You've got floating object here, and you have got bottom wall. Both as patches are accepted here. Yeah. So apply up, apply, and just you can see set it to be you. Okay, solve the problem, and you see that we have got the motion over here. The body starts oscillating. Oh, that's the problem with the power film. Okay, that's the velocity field. That's the hydrodynamic pressure field, and you can see that waves are again generated around the body, and you've got the free surface elevation on the upper boundary. So that's it. Okay. So again, we can solve the problem. So you can again sample the free surface elevation around the body very easily, and you can get again the free surface elevation and the waves that are generated around the body. So in another example, just let's change this problem a little bit. So what we did here was that we set the problem to be just dynamic. Just I forgot to tell you that just everything is the same. Just for the case of the control dict directory, you just set the solver to be this application to be potential for surface DynFOAM because you've got dynamic, yeah, or like other dynamic cases. And just to make the problem a little bit different, I just need a couple of more minutes and I'll talk about it. Just let me close this. I'm a little bit messy. Okay, so let's go to another example. And this time, let's set the body to have horizontal motion or longitudinal direction, longitudinal motion. So, right, instead of having vertical motion, what I do here is just going to another example, which I prepared for you, is example 4. Okay, what I do is everything is like the previous steps, what I did in what they have already done for all, what they had already done for us in tutorial. So we've got everything. So block mesh is the same. Just we've got the same problem domain. So we use superset again to exclude the box from the domain. Yeah, that's a box. I just shifted the box to the center because I want to have the longitudinal motion if it's near the left end of the domain. So if it's very close to the left end, so simulation might crash. So I just shifted it a little bit forward. So it used to be, I think, at 0.1 to 0.4. I just switched it to 4.5 to 4.4. And I just get again the bottom. And what we do here is just in the point displacement directory, what we do here, we just change them, switch this boundary of the floating object and floating object bottom. So this time on the bottom, we're going to have the normal slip in y direction. In the previous case, we had it in x direction when we had it over here in the previous example. And for the case of the floating object, we prescribe the motion, and look, this time the amplitude comes over here. Yeah, this is the x direction. So we have the motion in x direction, not z direction. You can have the mixture, but I'm sure simulation will crash if we do it at the same time because we haven't done the setup for such a problem. So you set the amplitude for vertical direct for the longitudinal direction, and again you've got omega, which is the angular frequency. And you just solve the problem, and just everything is and you just do it again for the case of the velocity. So for the case of the floating object, you've got the moving wall velocity on the floating object. So it's a dynamic boundary, yeah. So we just set it to go, and yeah, just set the problem to go, and the problem goes, and you see again we've got a dynamic motion, a problem with dynamic motion. Boundaries are moving. You have the solver is regenerating the mesh, the mesh, and recalculating the position of the grid, position of cells at every single moment. But simulation is super fast. You see, it's very fast. Okay, so it's again, sorry, that's the problem with my thing. So perform. Okay, and that's it. So let's just get the hydrodynamic pressure, speed, and zeta. Okay, see whatever you want. So I just want to have velocity field and okay. Oh yeah, I shifted the body to here because I wanted to have longitudinal motion. And what I get over here, I want to get velocity and just so that's the problem always. Yeah, you see that the body is having horizontal motion, and that's it. You can see that it's having horizontal motion, and you can see that we can have water waves. So that's it, and we're done with what I wanted to tell you today. That's water waves. Oh, look, waves are a bit, I think, larger compared to vertical motion, and it makes sense to me. We've got horizontal motion, waves are probably larger, so it's more, we can have larger waves. By the way, so that's it. So what we learned today is that, I mean, from this one, from the current presentation, is that we can use just a free surface potential form, this very, very good solver, to get very good potential free surface form, to get very good results in very fast simulations for the case that we don't care about having two phases. We're going to have this one single phase, and then we can solve the problem in a very fast way. And just to tell you something, it's acceptable to use it when motions of the body are very small, and it's got a sort of linear motion. So when the body is having a very, very large motion, and when we're going to have air-water interaction, so it cannot work. So it's better for you to go and use to switch to just interform or other solvers that you can choose, but you should not use a single phase fluid simulation in the case that we have got air-water interaction. In the current stage, we assume that there is no interaction between air and water. And so just a very important question, a very interesting question for you. Think about it. Can we use this solver to generate any type of waves we want? So think about having nonlinear waves, having nonlinear Schrodinger waves and other types of waves that might exist in physics. Yeah, can we generate them in water waves, in water environments by using this solver or not? So just think about it. That's a good question. You can think about it. Okay, I'm done with it, Tom.
Okay, thank you very much. Do you want to stop your screen share? We've got a couple